Hello AP Physics 1 students, welcome to another chapter. We will be discussing this common and important type of motion that you would usually see. Water waves, a spring, scales, when you pluck a guitar string. Also some reasons why this bridge collapsed over in the state of Washington in the 1970s, I think. Um, in your AP Physics 1 exam, you're going to be discussing this in terms of oscillating quantities, or also called periodic motion, or simply called SHM, or simple harmonic motion. So they are going to show you two common examples, and that's going to be the cart attached to a spring, or a vertical spring with a mass hook into it, or a pendulum. So what is common in here is that this will undergo repeated motion. It's because there is a restoring force that will cause this to go back and forth. So we could see that's the equilibrium position due to the force being 0, and equilibrium positions of that as well in this one. And we will try to understand why it's simple. It's simple because it uses a simple mathematical function, which is the periodic function. So the periodic function, which is a sinusoidal, that means it has the sine curve. So the sine function. So if you have that back in your math, so you will have, this is the equilibrium position, it's a function of time. So if you have a sine, that means the displacement, so this is the displacement. Displacement would be 0. So that gives you a sine theta graph. And then in terms of cosine, so it starts at a certain displacement and follows a sine pattern as well, only that its displacement is not equal to 0 for a cosine theta graph. So that's what makes it simple, because it uses this simple concept in math. So we're going to apply that understanding in analyzing this, which is a common example they're going to show you in AP Physics 1. So let's find out what are the dynamics in simple harmonic motions. So in order to understand oscillating or sinusoidal motion, we are going to look at in terms of amplitude. So what is amplitude? Amplitude in simple harmonic motion simply means it is the maximum displacement. It is the maximum displacement. So what is that? That's the maximum displacement is the distance from the equilibrium position to a positive or a negative displacement. So let's say, for example, I have this object here with a certain mass attached to a spring with a particular stiffness, and say the mass doesn't change, stiffness doesn't change as well, and I apply a force and displaces it. So from here I apply a force, and the displacement from here would be opposite of the applied force. So that gives me a maximum displacement. If I let go of it, it's gonna go back because there is a restoring force. So if I apply a force, this spring will exert an opposite force that is negative. When I let go of this, it's gonna go back and will have its maximum compression, which will give a force in the opposite direction. So that's how we look at in terms of amplitude. So given that it is the maximum displacement, same thing with this. So that is the displacement. So when we put a mass in that, there's no displacement in there. So this is its equilibrium position. Okay. So what will be the unit of this? Since it's directly proportional to the maximum displacement, its unit is in meters. Its symbol is uppercase A. So in order to find the amplitude, which is directly proportional to the displacement, we could say it's multiplied with the periodic function cosine theta or sine theta. So cosine theta if it starts at a certain displacement. So if we move this spring, so it starts at a positive displacement, so that's negative, the left side of the equilibrium position. So its equilibrium position, this is where the sum of the forces becomes zero. Therefore, there is no motion at that particular point because the sum of the forces is zero, or the net force. So in that case, you have a displacement with that amplitude. And then we know that theta in circular motion is equal to the product of angular velocity over time. And we'll know later that this one is related to the circumference, right? So which is 2 pi over period. And then we have another equation for finding the displacement, which is A cosine 2 pi over t times t. And then we will just replace this function depending on the type of sine we have. Over t. So another concept that we're going to be looking into this simple harmonic motion is how often this object will continue to make this cycle. So that is what we called frequency. So how often does this make that back and forth motion? And that is called frequency. So we write it in lowercase letter f, frequency. So frequency is the number of complete oscillations. Number of complete oscillations in a given time, usually in seconds. So the unit for that would be vibrations per second, or cycle per second, or oscillations per second. So say for example this object moves back and forth at a certain time, say 5 cycles in a second. So that is frequency. There's another most common unit that we're going to be using, which is Hz, or hertz. So 1 hertz is equal to 1 vibration per second. So that's another quantity that we're going to look into. Another quantity that we're going to look into is the time interval to make 1 vibration. So 1 vibration is when it goes back. So if we stretch this to here at A, it's gonna be restored back here by that restoring force, and it's gonna go back to A, and that is the time interval to make one vibration. So that is considered one vibration, and that is referred to as period, a symbol for uppercase T. I don't know why they represent period with uppercase T. So, you know, physicists. So that is different with time. Time is a variable. Okay? Although they have the same unit, this one is uppercase T. The uppercase T is a constant in simple harmonic motion. So take note of that. There is a relationship between the two, although that doesn't mean they are a proportionality. So the period is the reciprocal of frequency, and so frequency is the reciprocal of period. So in AP Physics 1, they want you to know how this oscillating quantities such as amplitude, period, frequency are related. So they're going to constantly test you on how do you see their relationship in terms of simple harmonic motion. So how do we find the restoring force given that the object is oscillating? So how do we find the restoring force? So we go back to this concept. So if we apply a force, say we compress the spring, so at this point the velocity is 0. Given that we apply the maximum force here, which is directly proportional to a negative displacement relative to the equilibrium position. So we given the maximum force, we take note the acceleration here is at its maximum. When we let go of the spring, the acceleration will be maximum. As it passes through the equilibrium position, the acceleration becomes 0. And then it goes past the equilibrium position, and what happens is that the acceleration goes down and the velocity goes up, and then the process does the reverse. So as the acceleration, as this object goes towards the equilibrium, what happens to the acceleration? The acceleration tends to go down, but the velocity increases. The velocity of the object increases. And same thing that happens at this particular point here, this particular displacement in here. So when it reaches its max displacement here, the velocity becomes 0 again, and then the acceleration will be at its maximum but will go slower. It will decrease, and then the velocity will be the opposite direction of the acceleration due to the restoring force ability to cause that motion. So we take note, look at the velocity here. It's gonna be the maximum. So the velocity, as the acceleration decreases towards the equilibrium position, what do you notice with the velocity? The velocity increases, and it reaches its maximum magnitude when it reaches the equilibrium position. So in this case, we notice that the displacement is directly proportional to the force, the restoring force, only in the opposite direction. So we would apply this concept as it's directly proportional to the stiffness. K is the constant, so that is the stiffness of the spring. So that's the type of the spring. X is the displacement, which is directly proportional to the amplitude, whether it's a positive amplitude or a negative amplitude. In this concept, if you could remember that, that is what we referred to as Hooke's law. So in order to find the restoring force, you just have to apply the Hooke's law. So how do I find acceleration? then we apply since there is applied force which will cause the acceleration, the maximum acceleration in particular, we apply the second law of motion. So the second law of motion, acceleration, let's play it at the max, and then the force will be at its max over mass. Now we know that the force is equal to Hooke's law, and we know that this one is equal to the amplitude, right? So we can replace that with the amplitude. So we can now have an equation that can be written down as this. So what happens if we increase the mass of this? Definitely, given acceleration is inversely proportional to the mass, given this, we know that the object's acceleration will be lesser compared to when it is less massive. But take note, the acceleration is at its maximum when the velocity is 0. And it will decrease. It will decrease as it passes through the equilibrium position, and it's 0 because the sum of the forces here is 0 as well. But the object still undergoing motion because of its velocity. So that is in terms of looking for acceleration. So another thing that we need to know how we could relate these quantities is how does mass affect the period of objects in simple harmonic motion, or how does amplitude affect it? So in your table of formulas or formulae, you will be given the formula for finding the period of objects in simple harmonic motion or periodic motion, and the reciprocal formula with frequency. It's right here, so you don't need to memorize it. If you wanted to know how this was derived, you can look at your textbook, or you can come to me and we will look into that. Although you do not need to prove how we ended up with this equation in an AP Physics 1 exam. You have to just understand how period is related with the other quantities. So we could see here that period is directly proportional to the mass. So what does it mean? The bigger the mass, the bigger the period. And what about the stiffness? So it's inversely proportional, right? So the type of spring, the stiffness of the spring, is inversely related to its period. So let's take a look at that in this particular scenario. So we have a spring. So given a constant K, let's see what happens if we put a 50-gram object. So you count the period, you count the cycle, you count the oscillations. So let's put it on a slow motion. So when it goes back to its equilibrium position, you can click it. Now let's compare it with twice the mass. So you could see that the bigger the mass means what kind of period. So you're going to do some labs and really try to provide this relationship and prove that this relationship exists. What about if we keep the mass the same and change the stiffness? So this is the regular stiffness. What happens if we make it larger? What happens if we make it larger? What happens if we make it slower or lower? Okay, so what relationship exists? So we could see here that amplitude is missing in the equation. So amplitude doesn't affect the period of an object undergoing simple harmonic motion. So particularly for spring. So this is a formula for finding the period of objects attached to a spring. So it is, we see that the period of the object undergoing simple harmonic motion is dependent on the mass and the stiffness of the spring. So another object that undergoes simple harmonic motion is the simple pendulum. So here is the mathematical equation. So quantitatively analyze the pendulum, the simple pendulum here. But we could also look at the relationship, the quantities on terms of the relationship. So we could see here that in terms of a pendulum, so the pendulum is, the period of the pendulum in particular is directly proportional to the length. So that's the length. So the longer the length, the longer the period. The shorter the length, the shorter the period. And then we also look at in terms of gravity, the acceleration due to gravity. It's inversely proportional to it. So that's the qualitative description on that. So that means the greater the gravitational force being acted on the object under simple harmonic motion, that is a simple pendulum, then we know that the period will be inversely affected. So take note here, the theta is small enough. Okay, so that's gonna be, and also the restoring force is proportional to mg sine theta. Well, technically it's just sine theta. So that restoring force is proportional to, or rather, take a look at this pendulum here and see the difference between a shorter length with a longer length. So the length is proportional to the period. What happens if we change the gravity? So it's changed the, this is the regular Earth. What happens if we change it to Jupiter? So that is the concept of simple harmonic motion. This is just the overview topic. We're gonna understand this when we do problems in class, and that's it.